think I'm ready.
Okay. So I think the way I'll present this stuff is sort of the way that I saw it. So I'm going to share my screen. And so there's the new, sorry, I'm now on something called Mastodon, which is a kind of social media thing. And somebody there was sharing something about ideal class groups. And so then I talked about it with Minyoung Kim, who's over here.
Yes.
And he helped me understand it.
Yes.
But I don't think I understand it well enough to just explain it.
Right.
Which would have been better, but anyway, so I will do it this way. So there's a guy named Mickaël Montessinos, and so he says, there's a fact about Dedekind domains that I find amazing and barely discussed. I'm curious how well known it is, so please let me know your thoughts. So take a Dedekind domain A, and then form its algebra of n by n matrices, MNA. So that's an algebra over A. And then take the group of outer automorphisms of that algebra. And that, he claims, is the n-torsion part of the ideal class group of A. So that struck me as cool and interesting. It reminded me of...
Well, that's what I'm wondering. Go ahead. What does it remind you of?
It reminded me of this Brouwer-Noether-Hasse stuff relating division algebras and central simple algebras and...
Yeah, none of these things do I really know as much as I should. But okay, yeah. I thought you were going to suggest another thing that it's vaguely reminding me of.
Okay, well, tell me what it is.
I can't remember the name of it, but it was like when we were studying Néron-Severi stuff, and then there was these Jordan algebras and stuff.
Oh, yeah.
That's a very vague connection. But anyway,
yeah,
that's
maybe.
what I was thinking of.
Yeah. I'm gonna.
So yeah, I'm not sure. I'm not sure what my reaction to this is in terms of number theory. It sounds very interesting, but I'm not sure I have any understanding of it yet. I can't even tell whether it's something I should already understand or something I've never even approached.
Yeah. So I will, by the way, skip certain sentences of him that I find actually confusing. So, I've seen a couple of independent proofs of this fact, sometimes limited to Dedekind domains embedded in a global field. But my favorite is the proof using cohomology. And I know I like cohomology better than you, but I did like, my ears perked up when I heard this. So,
yeah. So
consider the following exact sequence of group schemes. I'm going to try to avoid all technical details, but so
I do have a couple of questions about semi-technical details, but go ahead. Yeah.
So here's the multiplicative group scheme GM, which is like some very abstract.
Oh, okay. The multiplicative group scheme. Okay, fair enough.
Abstract incarnation of like the.
I mean, how is that different from GL1?
It should not be at all different from GL1. Yeah.
Okay.
So yeah, so it's included in GLN diet in the sort of identity matrix kind of way, and then its quotient is PGLN. So then they're going to use.
Sounds very plausible. I think. I don't know if there's anything I could possibly worry about here, but I'm not worrying about it. Go ahead.
Well, like when they say in the Zariski topology, that makes me like
sure. Yeah. Right. Okay. Yeah, that's tough to worry about.
Yeah. Actually, the worries, I guess, but anyway, yeah, I don't really want to worry about
Yeah.
anything other than there'll be enough to worry about that I have to worry about. So okay, so we're gonna treat these as coefficient groups for cohomology. Since some of them are non-abelian, like these latter two, then that means they'll only be good for cohomology for fairly low dimensions of cohomology.
Say that again. I'm sorry. I got distracted by something I was trying to figure out. But go ahead and say it again.
Since two of these guys are non-abelian, these two here,
Yeah.
we are only going to be able to use them for cohomology coefficients for very low values of cohomology, unless we do something far out, which I'm not going to do.
Sure.
So-
Sure. It's some unstable regime. Okay.
Yeah. So we're staying in the relevant regime. I guess I find this slightly misleading here. So we're taking cohomology sort of on the scheme corresponding to our Dedekind domain A. So we think of our scheme, our Dedekind domain is like a little space, that's kind of a space. And then we're taking.
Okay, A wasn't involved in the story at all until just you introduced this thing here.
Right. I mean, it was in the story originally. It was A is our Dedekind domain, blah, blah, blah.
Oh, okay, that story, but we're starting, okay.
But then, yeah, so this stuff here is sort of abstract and schemey.
Well, can I just make one comment about that?
Sure, yeah. So,
yeah, I mean, you're commenting on how group schemes in the Zariski topology sounds like annoying stuff to worry about. I mean, in fact, so far, I'm not seeing anything that's not just something that to me seems like a much simpler thing, which is just an affine algebraic group. All three of these are affine algebraic groups. And,
right. Yeah, that's true. And in fact, yeah, that's fine. That's true.
Okay, so that may come up, maybe.
Yeah.
Okay.
So, yeah, it sort of does. Some simplifications arise due to that.
Okay.
It wouldn't be true for like more interesting schemes. So I find this, I guess, now that I think about it, a little confusing. Now I realize why I was so confused. But I would call these first two guys H0 of A with coefficients in whatever. So I'd say H0 of A with coefficients in GLNA, H0 of A with coefficients in PGLNA, or maybe just
that makes sense.
PGLN, and then popping up by the connecting homomorphism going to H1 of A with coefficients in GM, and then H1 of A with coefficients in GLN.
Yeah, that's sounding like it's going to make sense. I mean, all these things I have to go home and check and see I'm not making stupid
Yeah,
mistakes.
well, so do I. I just found this, I like trying to learn this stuff, but I like learning it here and there. So so this thing I actually sort of vaguely knew or believed. So like if we were in a more I knew what it was, or believed I knew what it was. So if you think about it,
it does sound very ideal class groupish.
Yeah, so this is the ideal class group.
Yes.
So yeah, so if you
that sounds very plausible.
Yeah. Okay, so if you think of like,
I have to think about the details, but yeah.
So I mean, just sort of some stuff that that's sort of like some metaphorical hand waving is that H1 of a space with coefficients in some.
Yeah.
Well, like with coefficients in invertible complex numbers would be classifying line bundles on that space. And so, or you could, so this is like something like line bundles.
I mean, if you do it the right way, it's not really hand waving. It's really perfectly legitimate, and we've even come close to doing it that way ourselves at times.
Yeah. So then you can think of line bundles as being another way of talking about invertible modules, or invertible projective modules, but they're all projective. So yeah. So that's that. And then for the similar reason, and that forms a group. They form a group. But then there's this guy here, and this would be like in a similar
Sounds
way.
like it sounds like it's trying to be some kind of vector bundles or something like that.
Yeah. So this would be like,
again, how unstable is this? How stable?
yeah. So this guy's just a set now.
Yeah.
And so it would be the set of isomorphism classes of n-dimensional locally free modules. Or I guess for projective modules over a commutative ring, you can talk about the rank at any point.
Yeah.
Dimension of a vector bundle. And so you can talk about a projective module being of rank n everywhere. And that's like so there's that analog of an n-dimensional vector bundle available to you whenever A here was any ring at all, any commutative ring. Yeah. So that's what's being, those are the things being classified by this. And so this map here, what it's doing
again, right? So much of this can be, I was going to say, improved on by doing it in a 2-rig setting, but
yeah, that's part of whether or not improvement. I like it, and so that is part of why I got interested in this. So then this map here is taking. I'll talk, since I'm talking to you, I can talk how I think, which is think of it very geometrically. So taking any line bundle and taking its n-fold direct sum with itself and getting an n-dimensional vector bundle. That's a way to think about what's going on there.
Sure. Now that you remind me of what that homomorphism is on the left of the short exact sequence. Right.
Yeah. So it's
mapping
a number to a matrix with that same number down all down the diagonals. So yeah. So that's what.
Yeah, it's just kind of external tensoring with the n-dimensional vector space.
Right. Mm-hmm. Yeah. Or n-fold direct summing with itself. Yeah. So
yeah.
So then the kernel of this is interesting to conceive of. So there it makes you think about.
Oh well, it suggests already that bit about the n torsion, but go ahead. Yeah.
Right. So anyway, so this is going to be like the kernel of this will be like represented by line bundles whose direct sum with themselves n times becomes trivial. So they could have like a twist themselves, but somehow it's a kind of twist that manages to cancel out when you direct sum it with itself n times, and that should also remind you, that should also start reminding you about like sort of start reminding you of n torsion in the ideal class group, except there's some weird twist going on because.
Wait a minute, as opposed to what? I thought that's what you said it was. N torsion. You said this is n torsion in what?
Well, this is we're eventually supposed to get this by analyzing this. We're supposed to get n torsion in somewhere n torsion in the ideal class group is supposed to pop out of this.
Okay, but at first I thought you were telling me that this was it already or something.
Well, but there's a trick. Yeah, so the trick is that when you.
I must have missed some magic words that you said. Well, go ahead.
Well, yeah, I was like trying to trick you. So I was saying stuff that was all true.
Oh, okay. Well, it worked. Go ahead.
But I'll reveal. I mean, I'll tell you what the trick is. So the problem or whatever it is. So the kernel of this is like one-dimensional projective modules that become trivial when you take their n-fold direct sum with themselves.
Yeah.
But the n torsion in the ideal class group, the operation in the ideal class group is not.
Oh, tensoring?
It's.
Well, yes. Okay, yes. I guess you're right, but there is all sorts of tricks going on there.
Right. So there's, yeah, so there are tricks that manage to make them quite, yeah, there are
I mean,
tricks that
if
manage
you wanted to, you know, I could remember these tricks in like less than a few hours if you wanted to sit here and watch me try to remember. Go ahead. Yeah.
No, I don't.
Okay.
So, yeah, so, I mean, but there's a trick there that is
I mean,
required.
we talked about these tricks a long time ago. Go ahead. Yeah.
Yeah. So anyway, that kernel is very interesting.
You know, I mean, I'm sorry, it did really have to do with, right? We did talk about some way of thinking of an ideal class group as a K-theory group. And could be that be what you're hinting at here?
I'm
well,
that would be what I mean, that would be.
I'm groping for, you know, pulling things out of thin air without really thinking about them. But go ahead. Yeah.
That is the issue anyway. So the K theory would be to take all the vector bundles and use direct sum on them. And here we're just in the ideal class group, you're focusing on line bundles and taking tensor product of them. But here we're looking at line bundles, and then here we're taking direct, in this map, we're taking direct sums of them. So yeah, anyway, there's stuff going on. Yeah, so anyway, the kernel of that map is going to be the image of this previous map.
Okay, I don't have a good sense of that previous map yet. Yeah.
Right. I guess that's the tricky one in a way. The connecting homomorphism is always a little bit tricky. So I don't know if I understand it intuitively yet. So I will go on. Some of this stuff really confused me. And some of this is what stuff I already said. So like this latter sentence is just what I said. Anyway, go ahead.
Yeah, there's a couple of possibly comments of questionable relevance, but I think I need to say them anyway. So let's see, what was I going to say? So, okay. So first of all, what you were just saying about how PGL, you know, the image of that thing from PGL and of A, in some vague, very vague sense, that reminded me of stuff that I was reading about when I was trying to understand, you know, when you were trying to teach me about gerbs. I don't want to get into that right now, but I just wanted to make that silly comment.
Yes.
And then another comment I wanted to make, if I can remember it, is what? Right, this possibility I won't remember my comments here. Let's see. Let's see. Oh, I was going to say that in a way, what the focus or the concern with N torsion here, that is vaguely reminding me, as it sort of seems like, again, if I believe what I was saying earlier about neuron severity groups being neuron severity groups and stuff like that being connected with ideal class groups and line bundles and stuff like that. When we were trying to understand neuron severity groups of Abelian varieties, we were like, or at least I was, but I think there was like a complete non-focus on torsion. I think because it just, you know, the setup was that it just didn't show up.
Yeah, I think for Abelian varieties, it just didn't show up, and then for more general things.
So this situation is now causing us, trying to force me to learn some completely opposite flavor of stuff, where you actually do think about torsion in the line, line bundles.
Yeah, right. So of course, for ideal
that was just a silly comment that I wanted to make. Yeah.
So for ideal class groups of number rings, aren't they all? This shows. I'm going to reveal.
They're all torsion. All torsion because it's so finite.
Yeah, aren't they?
I guess you're right.
So
yes, you're right.
So here, well, at least like when A is a number ring, there could be it can be very interesting to look at the torsion. And one thing that I didn't get into, and this guy didn't get into yet either, is like, can you assemble all these n torsions for different n by means of some kind of limit to get, you can get like a pro-finite ideal class group, which might in some cases just be the ideal class, or maybe like in all the number ring cases, it might just be the ideal class group.
Or even if it isn't, which could still potentially be very interesting. Yeah, that's interesting.
So there's that.
What?
Yep. So there's that. Okay.
I have one more comment, unless you really want to try to plow ahead.
Well, I sort of do, but
well, so it's more of a question to begin with. Dedekind domains, you're not particularly concerned about that generality, or you're not particularly concerned about whether we're dealing with Dedekind domains or number rings, or maybe you are concerned with it. I don't know. I mean, well, I was gonna raise the issue of geometric or quasi-geometric interpretations of what Dedekindness means, in terms of like the spectrum or something like that. Do you have any ideas about that? Or I could tell you my silly ideas about it, but I don't have to. We just plow ahead.
Let's plow ahead, and then maybe like right at the end, I'd like to. It is something I want to know about, but I.
Okay. Go ahead.
So some of this stuff I found very confusing at first, but in fact, a lot of it. so the main interesting thing. Well, there are a number of interesting things. So one thing here is that, like I said, you shouldn't have really called this PGLNA. You should have called it H0 of A with coefficients in PGLNA.
With coefficients in PGLN?
Sorry, in PGLN. Yeah, sorry, in PGLN. And the interesting thing is that isn't. You might think that just was this isomorphic to PGLNA, because H0 is about global sections, and you can certainly get global sections of a sheaf of groups like PGLN over A just from a constant sections. So I believe the way it works. I believe the way it works is that H0 of the thing that really should be sitting here, H0 of A with coefficients in PGLN, elements of PGLNA are included in there, but there's more stuff.
Well, I mean, this is, what am I trying to say? That the ideal class group actually affects the interpretation of what projective spaces are.
Projective spaces? For such rings.
Well, I probably mean something like that, but maybe I shouldn't worry about that right now. But I just had a feeling that it was related to what you were saying, but I'm not sure how well I was following exactly what you were saying. Go ahead.
Well, so I'm saying is that writing PGLNA here is actually wrong. So it's not just like it's not just that, like, oh no, it's some other isomorphic thing, but it's something really quite different. So it turns out that so like I said, well, I'll repeat yet again, what obviously should be in here is H0 of PGLN. But then, so that's just obvious, but the cool part is what that winds up being. That is what that winds up meaning. And I was very confused. And then Levin LeBrun showed up on this discussion. I've never actually talked to him before. And he said that what you really get here is the group of outer automorphisms. Wait a minute. Sorry. No, let me say that right. No, what you get here is the group of automorphisms of the n by n matrix algebra over A. The group of all automorphisms of
right. I often think of that as being PGLN. Because in very vanilla cases it is.
Right.
Like over field.
Right. But here it turns out,
or at least is it over any field? Anyway, over very vanilla, in very vanilla situations, but that's just the same thing.
Right. That's part of the discussion we had of the confusion there. So yeah, and so in those, I guess, yeah, for a field, it probably they are the same. And those are the wait, let's see, is that true? No, if I don't believe that.
That what?
Oh, sorry. Yeah, they're the same if you think of them as, you're right, they're the same if by automorphism we meant like A algebra automorphisms. Yeah, but it turns out that in this kind of situation, this numbering situation, there apparently are other automorphisms, namely outer automorphisms.
Well, I was going to say, at some point I should really try to ask about what outer means in the context that we're dealing with here.
Well, I mean, whenever you have an algebra over some commutative ring, you can talk about automorphisms of it. And then you can talk about inner ones, which are ones given by conjugation with an invertible element in the algebra. And then there may be others that are not inner. Does that make sense?
Quite possibly. I'm just getting distracted by some things. I keep on thinking about, when we think about isomorphisms between projective geometries and which ones come from.
Right.
I wonder if that's related to this in any way. I can't tell if it is.
I was getting a little confused a bit because, for example,
yeah,
like even when you have a field,
yeah,
and you look at its matrix algebra,
yeah,
you look at that algebra as merely a ring, it'll easily have lots of outer automorphisms, like coming from the Galois group of the field.
Right, right.
But those are not.
That's not an issue.
Those are not algebra automorphisms where we're
right.
thinking as algebras over the field. So,
okay,
so those
maybe
first kind are very important in projective. I mean, you often run and hear about those in projective geometry. Like working over a field, you get, like complex conjugation gives this map from projective space to itself that's
yeah.
Or why did I bring in projective space? But it gives a map it gives a ring automorphism of the n by n complex matrices. Just conjugate each entry that's outer. Yeah, but here this is like a more exotic phenomenon that we're running into, because it doesn't happen, I guess, with fields. But for Dedekind domains, you can have outer automorphisms that are actually algebra automorphisms. Yeah.
All right. A lot of things I'll have to think about here that I haven't thought about before, or just not really getting yet.
Yeah. Well,
another thing, I'm suddenly worrying, should I be worrying in this discussion about, I mean, you said at some point, cohomology. Is there any sheaf cohomology going on here or anything like that?
Yeah, this
Or-
is all sheaf cohomology. Yeah.
So part of what you were saying then maybe was something about cases where these sheaves are actually just determined by their global sections or something like that. Were you hinting at anything like that? Because let's see, am I confused? Let's see. I mean, at one point you said ideal class group. You said this. Yeah, did you trick me into thinking, so this thing is the ideal class group?
Yep.
But you're saying it's a sheaf?
Well, GM is yeah, okay, there's like another subtlety, I guess, if you're not used to it. So we're by GM here, we mean the sheaf.
Okay, it's cohomology of sheaves.
Yeah. And we don't mean the constant. We don't mean the sheaf that only has constant sections that are elements of GM. We mean like the sheaf of GM valued, I don't know, what do they call them, regular or algebraic functions.
Sure, okay, yeah, okay, right. It's cohomology of sheaves. Okay, that part shouldn't bother me here.
Yeah. But here I'm just talking about this whole big fat thing is just like it's not a sheaf anymore. It's just a group.
Okay. Sorry, I was just getting mixed up about situations where
you might be able to do
itself a sheaf or something.
Yeah,
like
well,
that.
you might be able to do that, but we're not getting that.
Okay.
Getting that sheafy.
Okay, yeah, lots of things I'm not very clear on here, but go ahead.
Well, so this may never quite add up to enough of a good explanation right now, but I did get some clarity about this funny business, namely how the kernel of this map consists of line bundles. I'll call them line bundles whose n-fold direct sum is trivial, whereas in the ideal class group you're interested in line bundles essentially whose n-fold tensor power is trivial. That is, if you're looking for the n torsion in the ideal class group, that's what you mean.
Yeah.
So it turns out that those are the same. That those two concepts of triviality are the same, and so Mignon helped explain to me why they were the same, and it's some interesting stuff. So I guess there are a couple of funny facts at work here. So one of them is that let's see if I can yes, well, I don't know. I didn't have this very well prepared, but so like what he's saying here is that like when you take the n-fold direct sum of one of these, now I'm going to switch to algebraic language, modules, then that's isomorphic to a module where you take n-1 trivial modules. That sort of gives you the right rank.
Right.
And then the nth tensor power. This is like a tensor power.
Yeah.
And so
I'm saying with this with more confidence than I actually have, but it's really sounding like it's on the right track here. And it's really sounding like it is this stuff that we've talked about in the past. Trying to dredge up from memory here.
Yeah, maybe I'll stop here. There's more stuff that Mignon told me, but I don't think I'm going to do a great job of explaining. It was stuff that was like meant to be like explaining why this is true, which is so it's some of the stuff, I mean, I'll say it this way, some of the stuff is stuff that's sort of surprisingly nice due to the fact that you have an affine scheme where the twistiness of bundles possible is much less than for a projective scheme.
Yeah.
But then also some of it is special to the particular case of these Dedekind ones, which I guess you could think of as maybe some kind of low dimensional simplification.
Yeah, it's very much like one dimensionalness.
Yeah.
But there's, you know, some funny trade-offs between whether that extra one dimension is arithmetic in nature or geometric in nature.
So I believe that there are like a couple of things that work in this situation, this combined nice situation. One of which is that every vector bundle is isomorphic to a sum of line bundles. That's one surprisingly nice thing.
Say that again, what?
Every vector bundle over this scheme, which comes from a Dedekind domain, is a sum of line bundles.
I'll think about that.
So that's already true for like complex projective line. That fact is true, that there's like no kind of exciting higher dimensional bundles. They're all just sums of line bundles. But here, we get like an extra niceness due to the affine nature of things. And well, and I guess this extra thing is basically this fact that's stated here, that like the twistiness, I think it's even more generally true that the twistiness of any sum of line bundles can be all packed into one line bundle. I think you can just take the tensor product of all those line bundles and so that here they're all the same line bundle. If I had a whole bunch of different ones, you just tensor them all and you get like a line bundle that had like all the twistiness in it, and then a whole bunch of trivial bundles, and they would be isomorphic. I think that's what Mignon told me. I don't blame him. Do
you remember one time I sort of gave you a puzzle, which was something like, what's the exact sequence K theory of the category of abelian groups? I hope I'm saying that more or less correctly.
It sounds vaguely familiar. I probably.
So I think it turned out to be like, you know, an Eilenberg Swindle type puzzle that, you know, it turns out that K theory is trivial. Because of the exact sequence, you know, the exact sequences involving free modules.
Oh, you didn't say finite abelian groups. You said abelian groups, right? That's.
I said abelian groups, right? But should I have said finitely generated or something?
Well, we need some infiniteness, so maybe okay. Yep. Maybe finitely generated is enough to get this swindle to occur.
Yeah, I'm sorry, I'm being imprecise about that. But we had fun with that puzzle one time. You know, it was like, the reason I know we had fun with it is because I tortured you with it for like hours, because you kept on saying, you know, that, you know, first you thought it was just like, you know, had a basis consisting of the primes or something like that.
Right, that's what I thought.
Well, if it's not that, then it's got to be completely trivial or something like that. But you resisted the idea that it was completely trivial. And but now I'm thinking that, you know, like this, you know, this is the kind of thing that you do with a Dedekind domain. So what am I trying to say? That am I claiming that you get the ideal class group of a Dedekind domain by taking this K theory of the category of finitely something or other modules.
Generated projective modules. Yeah, I think that's probably.
Well, I'm worried about generated versus presented. I don't know. But
There's
oh,
one.
maybe Dedekind is where you don't have to worry about that. Were you going to say something? Yeah.
Yeah, I mean, I think you're right, except you also get, I think I ran into, while people were talking about this, a fact like that, but there's like, the K theory is the ideal class group direct sum Z, where Z keeps track of the rank of the module. So there's
Yeah, something like that, So, and I'm not trying to be too digressive here. I'm actually trying to be not digressive here. I'm trying to argue that somehow that thing that's on the screen there, that last thing that you were talking about Montessinos talking about, yeah, all that stuff. I'm getting the feeling that that is really closely related to what we were just talking about. But I'd have to think about it more.
Yeah. Huh.
All right. So you're going to say more stuff about this?
Nope. No, that's all.
Okay. Okay. What time is it now? What time we got?
It's 2:00.
Does that help me at all? That means like, okay. That means like we're halfway through.
Yeah.
All right. So I guess I'll try to say stuff now. And so, yeah, I could try to say stuff about this idea of the moduli stack of acute triangles, so to speak.
I'll be right back. I'm going to grab my notebook, which somehow I.
Yeah, I'm just going to try to take the screen and stuff like here. See if I can get this to work. It'd be good if I could find one of those pictures. I guess John didn't turn the recording on. Okay.
Okay. Sorry. Okay. Back.
Okay. So yeah, I'm also nowhere near as organized as I should be here, and I think that means I'm gonna, I may be like trying to tell a story, and I may have to repeat certain parts that I may have already said at some point because I'm not organized enough to not repeat those parts. So yeah. And right, and also right, and another way that this ideally could be done much better than the way I'm going to do it is I could have, one of the things I could have organized is, I could bring up beautiful pictures of all the pictures we're supposed to be seeing instead of going to be, drawing horrible approximate sketches of these pictures. So yeah, so right. There's this vague idea of the moduli stack of acute triangles. I mean, what do we even mean by that? What should we mean by that? And the idea that it connects to this more well-known, more precisely meaningful thing of the moduli stack of elliptic curves. So yeah, I'm doing this in a very unrigorous way. Let me start drawing some of these bad pictures here. So I'll draw the unit interval to start with, I guess. So I guess that's supposed to be the unit interval. And then I will draw a semicircle over it. Put a semicircle over it, sort of roughly. And then I'll draw these straight lines here, going off to infinity. And at that point, this region in here, that's kind of the locus of all the apexes. I don't really know what the word locus means or what it originally meant. The locus of all the, but I remember it from high school mathematics, they would talk about the locus.
Very sophisticated.
Yeah, the locus of all apexes of acute triangles over that interval. Right, I mean, yeah, right, there's that idea that these three boundary things tell you where one of the three angles of your triangle is getting insufficiently acute. And in particular, the semicircle at the bottom, that one is connected in some way with some famous theorem of Euclid's or something like that. So, and then we had this idea, well, and already to me, this picture already suggests hints at some connection to the moduli stack of elliptic curves, because there are things like this that show up in certain pictures that people draw, depicting how the moduli stack of elliptic curves relates to the upper half plane, to like a vertical strip like this in the upper, sort of like this in the upper half plane. So then, let me draw a little bit more here. Let me draw the quarter circle, something like that. Another quarter circle. Boy, that's, no, pretend that I did a decent job of drawing that. If it gets really bad, I'll try to. And let's see, and I guess, right, there's this one. So why did I draw those lines that sort of subdivide the that locus of the apexes of the acute triangles? Why did I draw those red lines subdividing it into 6 smaller regions? Well, it's because I may not have said what our goal is here, but our goal is here is to sort of invent a space whose points sort of correspond to all the possible kinds of acute triangles. And as we go along, we may say more precisely what we mean by that. But that's our goal here, to invent a space whose points represent all the different kinds of acute triangles. And so right off the bat, it turns out that we accomplished something pretty good, which is what every acute triangle in the world is equivalent in a reasonable sense to one of these acute triangles that's showing up in our picture. So we don't have to worry about not having enough of these acute triangles, but we do have to worry about having too many, because in fact each acute triangle is sort of overrepresented in this family of acute triangles. Each acute triangle is represented, well, generically, a generic one of these is overrepresented. It's represented 6 times in the picture. Basically because you can permute the 3 corners of the triangle any way you want, and it will show up again in the picture. And so that hints that maybe there's another way to draw this picture that we should be connecting. You know, maybe this is a good picture we have, and it's good. One of the things that's good about it is that it connects with the moduli stack of elliptic curves, but another thing that's really good about it is that it gives us a very explicit universal or almost universal bundle of acute triangles. Right? I mean, you just name a point in that region, and you just drop down these straight sides down to the unit interval, and that produces this acute triangle. So this bundle is very manifest in the picture, and that's one of the big advantages of this picture. But there's another picture which, there's a kind of conceptual trade-off. There's another picture which lacks this advantage, but it has some other interesting advantages of its own, which is, so this other picture looks something like this. It looks like, sorry. It looks like an equilateral triangle, which is already weirdly suggestive in a level slip way. And it's got it's subdivided into 6 regions in this way. I guess it's like the barycentric subdivision.
I mean, by the way, were you claiming that?
Yeah.
Were you claiming, without quite saying it, that the redundancy, the 6-fold redundancy of our original description is exactly captured by those red curves you drew on the left there?
Yeah, I'm saying something like that. I'm being very sloppy about it. Like the first time I gave this talk, I was really sloppy about it, and I'm probably still being very sloppy about it. But there's probably a few minor improvements that I'm being less sloppy about. But yeah, I mean, I was saying that, like, well, I mean,
yeah, it's sort of interesting.
So some of the things you're asking about now will be much easier to understand in terms of this second picture that I'm drawing. But go ahead, yeah.
Yeah. Okay, yeah, anyway, I probably believe it. So it's interesting to like think about like super skinny acute triangles. So it's very easy to see how they show up with points that are very far up the picture.
Yes.
And then it's sort of more hair-raising to see how they all show up near the very bottom of the picture.
Sure, but again, I think the second picture will really help in understanding. But go ahead, yeah?
Yeah, so anyway, it must, if that's what you're claiming, then it must be that any very skinny triangle shows up sort of both inside the red quarter circle, but really near the bottom of the picture, and also outside it. I wish I could point to the damn picture.
Actually, I mean, you might have just pointed out a sort of mistake that I made. What am I trying to say here? Let me get rid of that. No, let me get rid of that line. So really, I should have just.
Oh.
I should have just drawn that there.
Yeah. No, that's not what I was worried about at all. But yeah, I knew.
Okay. Yeah. So I mean, right.
Anyway, it's just.
I mean, underneath the semicircle isn't really there. I mean,
I didn't mean underneath that semicircle.
Oh,
I
okay.
meant the quarter circle.
Oh, underneath the quarter circles. Yes, that's right. It does show up underneath.
Like right down at the bottom of the picture.
Yeah.
There's regions within. There are 2 regions. There are 4 regions, but right near the lower right-hand corner of the picture.
Yeah.
There's like 2 regions there that get really close to each other because.
Yeah.
Yeah. So anyway, they're like, I guess like 2 incarnations of any skinny triangle, one on one side of that red line you're pointing at and one on the other side. And sort of nerve-wracking to see how they all fit in there, but I guess they do.
Right, it is nerve-wracking, but once again, when you undistort the picture and make the 3-bang symmetry much more manifest.
Yep.
Right. So, the thing you're talking about is precisely the thing that the second picture is advantageous for.
Okay.
Right. I mean, if you have, a tall skinny thing up here, then it's it's just gonna be there and there and there and there and there.
Okay.
And it's like that. But I mean, how do we even know that they're where am I getting this second picture from at all? Why should there be something like this? I mean, right. Well, so right. I mean, right, we're saying that when you look at the first picture, you begin to suspect that maybe it has some symmetry, but the symmetry is very distorted and hidden.
Yeah.
And it becomes much more manifest and clear in the second picture. But so, one way to see why that symmetry is there is just that, the upper half plane is equivalent to, the Escher or the Poincaré disk, or whatever you call it, right? And there's some tricks here, but it's going to work. So in fact, first time I gave this talk, I don't know whether I should consider this a mistake or not a mistake, but I mean, it was really a horrible mistake, but I knew I was committing the mistake. So I kind of, when I was giving the talk, I said, mumble, mumble, mumble. I'm not being very sloppy here. And that made it legitimate for me too. So the mistake is that, what did I say? I was saying something like that, mumble, 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 these pictures are like conformally equivalent. And maybe there is some way to make them conformally equivalent, but that's not really what should be going on here, I think. So what am I trying to say? That there's this picture of like well, okay, so right, I mean this little vertical strip that we've got here, that's just part of this Dedekind tessellation thing that we've been talking about, right? That Coxeter group, which is called the extended modular group or something like that. And right, there's an alternative way. There's an alternative way of drawing that. Right. I mean, what is the idea? That you can think of the upper half plane as like a sort of model of the, maybe it's called the hyperbolic plane or something like that. What am I trying to say? The Lobachevsky hyperbolic geometry, the Lobachevsky plane or something like that. Lobachevsky geometry, the hyperbolic geometry, where the parallel postulate works differently from the Euclidean parallel postulate. So, I mean, one way to, okay. So one way to draw this thing, one very Escher-like way to draw this thing is like, maybe I should really use a different color here, because I don't know if the colors that I'm using here are relating exactly to these other colors. So I'll use green here. So let's see, I think these are circles that I'm supposed to be drawing here. And then it keeps on going like that, right? And I don't know exactly the right way to draw it, but it keeps on going something like that. And it's the same Coxeter group as this upper half plane picture, which what does the upper half plane picture look like? So, it's just this thing that we already drew here, but it's got more of these vertical strips. So it's got like, I'm drawing this really sloppily. So what does it look like? Looks like that, and that, and that, and so how does this work? You have those semicircles, and then you have these. What do they look like? Sorry, that's really too sloppy. How far up does it go? And then, et cetera, et cetera. Boy, this is sloppy, but you get the idea, right?
Yeah.
And then there's also all sorts of fine detail inside of there, which I don't want to draw, but and this picture over here, picture A and picture B are conformally equivalent. And in fact, if you think about that conformal equivalence, it's really just, what am I trying to say? It's like by stereographic projection, you can think of the complex plane as the Riemann sphere. And the equivalence between A and B here is just, some very sensible rotation of that Riemann sphere under this stereographic projection thing over here. So, right, there's some very straightforward geometry going on here involving stereographic projection and the way stereographic projection makes the Riemann sphere secretly almost the same, secretly the extended complex plane. And so there's all that game.
Yep.
Yeah, go ahead.
Yep, nothing.
And I guess one of the magic words that's lurking around here is Möbius transformations and stuff like that. Yeah, so there's a nice conformal relationship between this upper half plane picture over here, picture B, and this very Escher, MC Escher like picture A. Again, hardly any need to remind you that all these pictures are very badly drawn here. But notice that, let's see, I guess if I really want to finish picture A, I should include, right? There's all these other lines that are important to include. Am I doing this right? I'm doing it sort of right, but I should make a little bit better than that, because otherwise it would be really bad. I'm trying to get these things to meet in the middle. Am I doing this right? Yeah. So, right, you can sort of see that there's this thing in the middle here. It looks a bit like my picture C over here. But, picture C is very straight-sided, whereas picture A has all these circle things over there. But that's also a famous known thing, but involves sort of violating the principle of conformal geometry, right? So, I mean, what am I trying to say? There are some famous competing pictorial models of Lobachevsky geometry. In one of them, the straight lines are the circles inside the disk that meet the disk at a right angle. Am I saying that right? I think that's right. You've run across that, haven't you?
Sorry, say that again.
You can get a model of Lobachevsky's geometry by taking the points to be the interior of the unit disk and taking the lines to be the circles inside the disk that intersect the boundary circle at right angles.
Yeah,
I hope I said that correctly.
Yeah, that's right.
So that's a famous model. Is there a name for that model? Maybe it's called the Poincaré model.
I think it's called the Poincaré model. There's also a Klein model where you use straight lines in the disk.
Well, I was going to say Beltrami-Klein.
Okay.
Or Beltrami-Klein. I think, like there's a Wikipedia article on the Beltrami-Klein model or something like that. And what did you say that one is?
That's straight lines in the disk.
Yeah. So the point is that that's what this thing looks like. Let me make it picture D, I guess. It's just kind of the Beltrami-Klein. If this is the Poincaré model, but the Beltrami-Klein model is picture D here, but it's going to look a lot like picture C. C is going to be kind of in the middle of picture D. So what does it look like? It looks like so it's just, these straight-sided triangles. Now one of the things that makes these pictures so badly drawn is I'm being very careless about where do these ideal boundary points, these corners, these cusps, where exactly do they appear on the boundary circle, it's not just evenly subdividing it or something like that. So, but from my picture, you couldn't tell that. Right, because this is like, you can sort of think of this as like a Stern-Broco tree type picture, right? You can sort of see the binary tree picture here. But, the Stern-Broco tree, right? It's not like giving you binary fractions. It's or what do they call it? Dyadic. It's not giving you like dyadic fractions. It's giving you all the fractions, and they're set up in a more interesting way than just binary subdivision, even binary subdivision. So yeah, so there's a big difference between picture A and picture D. A is the Poincare model, D is the Beltrami-Klein model. Now, one of the things that is in common between picture A and picture D is that I deliberately chose to make them Eisenstein-centric, right? I could have made them Gauss-centric or something, right? I could have put a vertex where 4 things meet in the middle, but I put a vertex where 6 things meet in the middle. So this is like Eisenstein-centered, Eisenstein-centric pictures of what's going on here. And there's a reason, there's probably a reason why I want to do that. Yeah, because I want this centerpiece of the picture to be this triangle type thing here.
Yeah.
So we've got yeah, so what was I going to say here about this Beltrami-Klein picture? Well, I guess I was going to say that there's this really big contrast between picture A and picture D. That picture D involves these straight-sided triangles, whereas picture A involves these curved-sided triangles. I guess actually circle-sided triangles or something like that. So it's a big difference between them. But there is one important thing that they have in common, I think. I hope I'm right about this. Otherwise, my calculations will be pretty screwed up. I think they agree on the boundary circle, where those ideal cusp points are on the boundary circle. I think that should be the same between the two pictures, and that should make certain calculations easier, I think, here. So what am I trying to say? I'm trying to say that, well, you can also put in these lines here. Again, this is very badly drawn, but that's right. I mean, right? You're already sort of getting the idea here, right? That even if I'm saying it really bad, that when we looked at this picture over here, maybe I should call this picture E or something like that. So when we looked at picture E, we saw that there was this 6-fold over-representation of each acute triangle. And that was hinting that the 6-element group 3-bang was acting on the picture. But in picture E, the action, if it exists at all, must be in some very distorted way.
Yep.
But if we really want to get picture E to look very simple, like picture C, then the suggestion is that we can just use this Beltrami-Klein picture of the hyperbolic plane to make this thing that's sort of like the moduli stack of acute triangles, to make it look simpler in a way, to make it simpler in a way, to make in this way that the 3-bang symmetry becomes manifest, and also the picture is somehow very simple. It's just a triangle. So that's the main conceptual trade-off between these two pictures, between picture E and picture C. That in picture E, the universal bundle is just built into the picture, kind of. It's just right there.
Yep.
Whereas in picture C, you can see the 3-bang symmetry is staring you in the face. So, in other words, so now what do I mean when I say this is the moduli stack of elliptic curves? Well, so what I really mean let's think in terms of picture C. So picture C, forget the red subdivision stuff. Just think of it as the black equilateral triangle.
Uh-huh.
So first of all, that's just a topological space. You can just think of it as a topological space. Now, in fact, there are all sorts of games you can play here with. There's so many different ways that you can think of this as a moduli stack or an orbifold or a Grothendieck topos. And for each of those choices, you probably have a whole bunch of choices of different topologies you can use. So like there's like, the ordinary topology versus the Zariski topology. There's all of these things, annoyingly confusing things that I don't want to worry about too much here. So I'll try to use, more elementary school type choices. So I'm just thinking of this as, well, I mean, maybe it's, I don't know, maybe it's more like freshman topology or something like that, because I'm thinking of this as topological space.
Mm-hmm.
But I'm just thinking of it as, an equilateral triangle, a closed equilateral triangle, although you can also focus on the interior. A closed equilateral triangle as a topological space, and moreover, it's a topological space that is acted on by the finite group 3 bang.
Yeah.
And so once you have that situation, there's various games you can play. One of the games you play is you can simply take the quotient space, the orbit space, mounting out by the group action.
Mm-hmm.
And right, so that's sort of countering this overrepresentation, this 6-fold overrepresentation, right? So that's right, that sort of does that. That sort of right. You could say you could just sort of write this whole equilateral triangle folds over on any one of these 6 sectors, and except for these annoying glitches on the fixed points of either fixed points of the whole group or fixed points of some part of the whole group. Except for those glitches, like where the isosceles triangles are and the equilateral triangle is. Except for those glitches, we've now got, sort of a perfect moduli space. Each acute triangle is just corresponding to one particular point in, any one of these sectors, which right, and there's all sorts of sort of gauge fixing games you can play here. You can just think of this, one of these sectors as a sub thing, but you can also think of it as more or less a quotient space. Mm-hmm. So yes, so one of the questions that like I say, when I first started telling people about this, I was very sloppy about, I would start drawing this picture E, and then I would say, mumble, 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 let's change it to picture C, because it's really probably secretly equivalent anyway. But now I got tired of just lying to people too much about that. So I really got curious about how to make it rigorous about what's going on here. So, now picture E is, rigorously this picture, and picture C is rigorously the Beltrami-Klein Eisenstein centric picture. And so we have this sort of universal bundle over in picture E. So it transfers over to picture C, right? I mean, I'm using the word universal bundle in a very sloppy way. You can imagine a universal bundle over a moduli space or something like that, but this is really a moduli stack.
Yeah.
Maybe I should call it a universal bundle anyway, but so, but funny things happen at the glitches where you have objects that have extra symmetry, the stacky points of the moduli stack, or the stacky points of the moduli space that don't really want to be part of a space, they want to be part of a stack. And so in picture E, we have this universal bundle, but picture E is, sort of cryptomorphic to picture C in a non-conformal way. And so we can just transport this universal bundle over to picture C. Mm-hmm. But it's, it was, that universal bundle was completely manifest in picture E, but now it's much less manifest in picture C, right?
Yep.
So one of the questions that I'm asking myself here to try to make myself be more honest about what's happening here, be more honest about my understanding of it, is I'd like to know, right? It's like I'm claiming that to specify an isomorphism class of acute triangles, you should specify a point, or maybe I should say, instead of specifying an isomorphism class of acute triangles, maybe I should say, let's take an acute triangle and let's artificially label the vertexes,
Right.
1, 2, and 3, and then we can say that this equilateral triangle is the space of sort of acute triangle structures on this abstract set of 3 corners.
Yeah.
But if I'm claiming that to be true, then what are these? So for example, there are these very nice coordinate functions that an equilateral triangle has, right? I mean, and it's these are barycentric coordinates, right? I mean, this was, or I think, isn't Möbius coordinates? The Möbius is maybe the person who invented the barycentric, one of the persons who invented the barycentric coordinates. So I mean, there's this coordinate function which is equal to 1 over at this corner, and it's equal to 0 at the opposite side, and then it's just linearly or convexly interpolated between there.
Yeah.
And so these functions are these barycentric coordinate functions are very natural functions to consider over in picture C. But we can ask to interpret them in terms of what is that, what is that telling us about the acute triangle? You see what I'm saying? Is this giving us like angle information at one of the angles, or is it giving us side length information, or what? So that's a question I set for myself to figure out, to see if I could really understand and get to make sense. Do you have the answer yet? Do you want to tell me the answer?
No, I don't. Not any interesting answer. I mean,
well, I don't completely have a really great answer yet, but I can make some progress on it, and that's one of the main things I want to try to tell you right now. Is so let's see. So okay, over here we're in this Beltrami-Klein picture D, and it's secretly cryptomorphic to all of these other pictures. So what am I trying to say? Or maybe I should say picture C and picture E are secretly the same. So what am I trying to say here? That maybe I should, let's see. Maybe I should try to draw these horizontal ones instead. So I think you can sort of see what corresponds to the horizontal pictures, the horizontal lines over in this picture. Sorry, did I lose a, that was supposed to be an E there. How did I borrow my E? Has that been missing the whole time? In picture E. Is it clear what the, what's the corresponding thing to the horizontal lines in there? What I think it is, I think it's these, it's all circles centered at 1/2, but of larger radius. So there's like, I'm doing this right? Is it like a circle, semicircle like that? And then there's another larger one like that. So this first semicircle, right? That was the semicircle of radius 1/2. And then the next circle is the semicircle of radius 3/2, and the semicircle of radius 5/2. Right? I mean, the center is right, is here, right? So am I doing this right? Let's see.
What's confusing to me, so I'm trying to figure out why that could be true. What's confusing?
Yeah, maybe I said it wrong. Go ahead.
I think I think you're admitting that there's not really a good conformal transformation between pictures E and C.
That's right. That's right. That's right. But
yet conformal transformations map straight lines to circles. So you're saying that like as if. So anyway, you're saying that whatever this map is does map these straight lines to these circles.
yes, because these are the straight lines of Lobachevsky geometry. Over in the straight lines in picture C are also straight lines in picture D, and those are lines, those are Lobachevskian lines. And the things I'm doing over in picture E, I may be getting them calibrated wrong. I think I said radius 1/2 and then radius 3/2, but I guess it's radius 2/2 or something. I don't know. Anyway, there are these circles of different radius, but they're still just Lobachevskian lines. So they're still, the Lobachevskian lines over here are corresponding to Lobachevskian lines over in this picture. So I think what I'm saying here is like, let's draw, a semi-typical acute triangle here. And so I'm saying that the line that it lies on in picture C is sort of corresponds to something. I want to, I'm trying to draw this. I'm looking at this circle and I'm putting this center of a circle, and I'm drawing the circle with that center, but through this point. So it's like up there or something like that. And it ends up being, down there or something like that. But you see, all the things on the same circle are distinguished by the distance of this vertex of the triangle to the midpoint of the opposite side. So I think that's right. That's not a final answer yet, but I think that's getting close. I think that we're saying that these coordinate functions over in this picture are some sort of function of this distance from the vertex to the midpoint of the opposite side.
Yeah. That seems sort of like a very weak statement somehow.
Is it really true? I thought it might be a stronger statement. I mean, I made a lot of progress in figuring out exactly what function of that distance it is.
Well, that would be.
But I'm not. But I'm not sure if I should try to say that in my remaining 15 minutes. Maybe I should try to say something else in my remaining 15 minutes. But okay, even if I don't give a good answer to this question, I just wanted to impress on us that this is a good question. For me, this is a good question. I'd like to know, right? We've explicitly defined what are these coordinate functions on the moduli stack of acute triangles, or more particularly, right? They're really just coordinate functions on the moduli. No, they're coordinate functions on the space of these acute triangle structures on an abstract set of 3 corners. And they're just these, barycentric, Möbius barycentric coordinate functions. And I'd like to know a nice description of their interpretation in terms of the geometry of these acute triangles. And I can't be sure whether you might be right. Saying that that's a very weak statement. Are you saying that? See, like I thought, there must be some way you can encode this structure in terms of pure angle information, right? All you have to do is just give angle, right? If you know the 3 angles at the corners, that's like a complete characterization of the. But you could also know the 3 sides, the 3 side lengths as proportions of the total length or something like that. And are those functions of each other? I was thinking those weren't functions. It sounded like you were suggesting that maybe all of these are just functions of each other or something like that. But I have a feeling that different ways of doing it may spread the information out from being concentrated at one corner to being more globally distributed among the three corners. Like, if you want to know the angle information at one corner, maybe you have to know the side information or all three corners and vice versa or something like that. But I don't know. I mean, suddenly you're making me think that there might be some. I admit I'm confused about this. But anyway, I still think it's a good question. I think it's a good question. And one of the reasons it's a good question is, like I say, it would, make me be more honest when I tell people this story about how picture E and picture C are sort of equivalent pictures of the moduli stack of acute triangles. So, yeah, so one of the things, I'm not sure if we said it out loud yet, maybe we did say it out loud, but if you've got this space of structures, that space of structures has, the equilateral triangle as a space of structures that has this three-bang action on it, right? And then you just take, right, you could just take the moduli space just by taking the quotient space under that group factor, but you could do more sophisticated things, right? You could, instead of thinking of this as a mere topological space, you can think of it as a Grothendieck topos, which is sort of a more sophisticated thing, because points in a Grothendieck topos can have automorphism groups, which, so to speak, represent the memory of what the neighborhood of this point was like before you quotiented out or something like that. Which again is sort of like this idea of an orbifold, right? When you create Grothendieck toposes in this way, by just modding out in a subtle way by a group action, it's very reminiscent of and related to the ideas of orbifold theory, except I think it's much, much better. To me, the idea of orbifolds represents like a sort of an unorganized feeling that we deserve to be able to remember, just by, there should be something better than an orbit space that remembers what happens before you mod it out by the action. So it keeps track of what's going on at the funny points, the peculiar points, the points with anomalous extra symmetry. But so one of the ideas is going on here is that, maybe instead of some what I would consider some very clumsy formalism of orbifolds that various people may have defined, you could just think of orbifolds as special kinds of Grothendieck toposes or something like that.
People are starting to do stuff like that. They're trying to clean up the theory of orbifolds.
Yeah, I think they've actually been doing it for a while.
Yeah.
But I think it's very straightforward. And, they just are much better thought of as Grothendieck toposes or something like that, or, these kinds of moduli stacks in some cases, whatever. So yeah, that's very much this kind of thing that's going on here. So,
so do you have anything to say about how this gets hooked up with how this gets hooked up to the elliptic curve? So it looks like the traditional moduli space of elliptic curves is twice as big as one of these little triangles. I guess that's just this usual thing about the modular group versus the, whatever you call it, extended modular group.
Yes, or in the other thing, it's, the three-bang versus the alternating subgroup, which is just the orientation preserving things of this equilateral triangle. So yes, right. That's another thing I'm being sloppy about, the issue of keeping track of the orientations or not keeping track of the orientations. And as you say, yes, that one way to deal with that is just kind of the extended modular group versus the modular group, et cetera, et cetera, et cetera. So, So like one of the things we're saying here is that, so first of all, let's try to say more explicitly what what explicitly, what is the Grothendieck topos that I'm talking about here? So it's basically, take that original space, when it was just a space, the space of structures, this equilateral triangle, the space of, take that, take the Grothendieck topos that corresponds to, take the so-called spatial topos that corresponds to that equilateral triangle. So that's just sheaves on the topological space given by the equilateral triangle. That's a spatial topos, so to speak. But now the way we sort of interestingly mod that out by the action of the group 3 bang here is we say, instead of, so what we say is now consider instead the 3 bang equivariant sheaves over that space. So now an object is one of these sheaves, but equipped with an action of the sheaf, an action of 3 bang on the sheaf upstairs that commutes with the projection down to the base space. So that's, those are the equivariant sheaves on this topological space with group action. And that is the topos that we're interested in here. And so let's, for example, and let's consider, for example, let's compare this and let's relate this and compare this to the topos given by the spatial topos corresponding to the circle, let's say, for example. Okay, so the circle, that's just another topological space. Right, and it kind of represents loops. In the category of topological spaces, it represents loops. And in the category of Grothendieck toposes, it also sort of represents loops in some sense. So what am I trying to say here? That we should be interested in geometric morphisms in the geometric direction going from sheaves over the circle to equivariant sheaves over the equilateral triangle. And if I didn't get it backwards, then that should, do you have like a naive pictorial conceptual geometric interpretation of what those geometric morphisms should be like? They're sort of like loops in the topos of acute triangles.
Right, but the triangles can come around back, like with their corners permuted.
That's right. That's right. Now let's notice, right? If you just did the coarser thing of just taking the quotient topological space. And then if you took loops in that, right, I guess if you, well, right, so, okay, so when I was giving this talk the first time, there was this audience member who, I won't even attempt to say his name because I'll just screw up his name, but he very helpfully suggested that you think of these loops in the topos of acute triangles as Toblerones that have been left out in the sun too long. Have you had a Toblerone? You're familiar with them?
Yeah.
Well, Toblerones have been left out in the sun so long that I guess you can reach around and join them up either with a Möbius twist or without a Möbius twist.
Oh, I see.
When I call it a Möbius twist, well, first of all, it's not related to those Möbius barycentric coordinates I was talking about. I don't think, but
it's
it,
also a triangular. Triangular.
yeah, it's an honorary Möbius twist. It's like a triangular
Yeah.
mod 3 version of a Möbius twist or something like that. And so like you say, you have an extra choice, an extra global piece of information that's not really there in the local information. So, and what we mean by that, right? What do we mean? What did I just mean when I said that it's a global piece of information and it's not there in the local information? Well, what I mean is, if you take this quotient space, if you take the naive coarse moduli space and you look at the loops in there, there is like a comparison thing there, so that, you know, from one of these melty Toblerones, you can obtain a loop in the coarse moduli space. But that loop in the coarse moduli space doesn't have the global information in it, right? It lost the global information.
How much information does it actually lose? I mean, a point would obviously lose information, but a loop, sort of like you still could.
How would
like
a point lose
remember
information? A point wouldn't really lose information. I mean,
yikes! No, you're right. That's true. Yeah, a point. But how does a loop lose information? That is, if I know,
yeah,
how my triangle's moving,
yeah,
and then it comes back to itself.
yeah.
From knowing how it's been moving around, changing shape.
Yeah.
It's like I could reconstruct whether it's come back with the same named vertices or different named vertices.
Well, I mean, in general, no. I mean,
okay.
I mean, like, I mean, supposing you have, you know, supposing you have a constant loop in the moduli space that's constantly at the equilateral point. It's the, you know. Then that's, you know, that's saying that your Toblerone is a locally trivial Toblerone of you know, with and it's like perfectly equilateral everywhere. But it's not saying that it's not saying that it doesn't have a Möbius twist in it.
Okay, yeah, you're right.
So, in fact, okay, so there's even, in fact, there's a little theorem here that I sort of like, which says that it's a sort of fixed point theorem. It says that supposing you have one of these Toblerones, one of these loopy Toblerones, and supposing, how do I say this? Supposing that it is not globally trivial.
Yep.
Then at some point of the circle, the fiber acute triangle must be isosceles. Is that obvious?
It sounds very believable.
Well, let me try to give an argument, which maybe could be made into a proof.
We're going to have to stop, by the
Sure.
way.
Sure. But yeah, but let me just try to say the argument. So you've got this Toblerone, and assume that it has no isosceles strings at all. Then that means that there's a globally longest side and a globally shortest side and a global middle side, and you can just comb the Toblerone, so it's topologically trivial. So did I say it? Anyway, we'll have to quit right there. There's probably some things I forgot to say, but we'll have to talk about it later.
Yep. Okay. Yeah. No, I get the proof. Even though combing a Toblerone is a good metaphor, but yeah.
Okay. So there's probably, you know, there may be things that you forgot to tell me from the first half of the discussion, and there may be things I forgot to tell you from the second half of the discussion. So we may try to pick up on some of these topics later.
Yep.
Okay.
Yeah.
I'll see you.
Yep.
Okay. Thanks a lot. Bye.